So the kind of research I do has to do with trying to solve questions about global points of elliptic curves or about units and number fields using techniques that have to do with modular forms. But what is very important to me is to try and get explicit formulas out of modular forms that involve some arithmetic invariance. So the setup of the questions I'm going to talk about is going to be very classical. I'm going to talk about this setup in Taylor Wiles, and all the modular forms that will appear here will have weight 1 or 2. Okay, but I'm going to introduce the question of describing generalized eigenvalues. And this project arose from a different question that had to do with trying to generalize conjecture of Harris and Venkatesh about the action of a motivic cohomology group on the cohomology of Shimura varieties to a much more concrete question about points, global points for elliptic curves. But so here is the setup. I'm going to start with an example, most classical example that you can think of. I'm going to start with the modular curve of level 11, which turns out to be an elliptic curve. And for this reason, there will be a unique cusp form of level gamma not 11 that I will denote by F. So this is going to be new form. With some few expansion. And for the coefficients of this new form, there is a well-known incongruence that tells us that the AL coefficient is congruent to +1 mod 5. So this is a well-known example, the most basic example that you can think of congruences between a cusp form and an Eisenstein series. So this implies the congruence between F and the unique Eisenstein series of level 11, mod 5. And this is telling us something interesting about the action of Hecke operators. If we look at the modular forms of weight 2 and level gamma naught 11, mod 5. So I can choose a basis. That mod 5 that is going to be given by the reduction of F, which is the same as the reduction of this, of the Eisenstein series, plus something else. And the other piece is going to be given by the difference of the two divided by 5. And this, sorry. This gives us a basis. I'm going to call this guy here F star. And yeah. Okay. Is that an okay size? Yeah. Okay, great. So if I want to look at the action of modular forms, Hecke operators over that module, in the basis I've given, I can check that EL will not act semi-simply because there is this congruence, but will pick up here some coefficient AL star. And a formula due to Mazur characterizes what this AL star will be as follows. So AL star is going to be equal to L minus 1 that multiplies the image of L under a discrete logarithm map, linearizing the group, the multiplicative group of Z mod 11. For every L prime different from 5 and 11. Okay, so this is the kind of formula I'm interested in discussing today. This map is a group homomorphism, and it turns out this in some sense will be the most general situation when looking at Eisenstein congruences. Shape of the generalized eigenvalues appearing in this upper right corner for Eisenstein congruences. At prime level. Meaning that the Eisenstein congruences arise for primes L that precisely divide the order of a group like this. Sorry, for primes P dividing the order of the groups of a group like this, so that such a discrete logarithm exists. And then one can expect like this action of the generalized Hecke operators to factor through this map that we described. Okay? So my question is, how does this formula generalize to other settings? What is interesting about this is that the image of these L's don't seem to really depend on the choice of the prime P dividing the order of this, in the sense that there is some general group to which we apply a map, and we get that we know very well, a discrete logarithm, and we get a formula. And in some sense, they don't seem to really depend on the level n either, because it's just the image of L under an appropriate map. So I'm interested in studying this question in a more general setting when looking at congruences, now not between Eisenstein series and cusp forms, but just congruences between cusp forms that arise from level raising. So, for example, I can put myself in the situation in which I want to take the same modular form F, but I want to find congruences mod 3. So 3 will not be an Eisenstein prime, but I can find congruences by raising the level at 7. And I can find a new form of level 77, such that G is congruent to F mod 3. And I can again ask the same question about what does the Hecke action look like on a basis of the mod 3 eigenspace. Now, the existence of this congruence is motivated by Ribet's level raising result. That tells us that if P is a prime different from 2 with additional assumptions, and P divides the order of, and P divides an squared minus n plus 1 squared, then I can find a congruence with an n new form, given my original one. And then in this case, the role of n is played by the prime 7, guaranteeing the existence of this congruence. So what's interesting about this is that this can be reinterpreted in terms of the number of points of an elliptic curve over, not quite at f7, but f7 squared, quadratic extension of f7. So the question is, can we also expect this Hecke action and this generalized Hecke eigenvalues to factor through a formula that has to do with this group? So let me fix some notation and say, given a new form, if I fix for an appropriate Hecke algebra T such that I have a morphism into FP, the question of finding this generalized eigenvalues really boils down to understanding the lifts of this morphism, sending TL to AL mod P to the ring of dual numbers. And of course, this kind of questions are studying lifts of morphisms into the ring of dual numbers are very closely related to studying deformation rings. But what I would like to know is how explicit can we make this formula really? So such a morphism will take for lambda f tilde which is going to be for a given Hecke operator, the L is going to be given by AL plus epsilon. I'm going to denote this generalized eigenvalue as AL star. And I want to know what I can say about the sequence of generalized eigenvalues. So this won't be well defined on the nodes, but we can rescale the whole sequence by a scalar in FP. But the ratio between different primes will be well defined. Okay, what is the motivation to look into this kind of question? So one interesting thing the motivation is one interesting thing that comes up in trying to address this question at non-Eisenstein primes is that we do see a similar behavior in which, in some sense, what comes out of the description is independent of P, and it is kind of independent of N as well, in an appropriate sense, meaning that there is we'll be able to see that there is some sort of universal object through which this generalized eigenvalues factor, and we get them through like very explicit maps. Okay? And I thought this would be an interesting question to discuss here, because I think this is, in some sense, saying things about deformation rings for different primes having something to do with one another in a way that is not conceptually clear to me. And I would be very happy if someone had an intuition behind what might be going on. Another motivation for me to look into this was that this question of studying this generalized eigenvalues turned out to be very useful in a different setting when looking at the generalized eigenspace in over convergent wave one modular forms. Attached to a classical wave one modular form. So in general, this generalized eigenspace will be bigger than the genuine eigenspace. And one can ask, what do the coefficients that appear there look like? What are these generalized eigenvalues? And it turns out, in this case, the generalized eigenvalues have to do with units, or more generally, S units in the field cut out by the Artin representation attached to a wave one form G. So this will factor. And this kind of, in particular, this units will be described in terms of certain p-adic logarithms of units for this field. And this has application to explicit class field theory. Here's a topic that Samit discussed yesterday in relation to the Brumer-Stark conjecture. And in some sense, like describing this generalized eigenspaces played into the Ribet's lemma sort of diagram that Samit presented in a slightly different way, because in some sense, instead of allowing us from going from cusp forms to Galois representations, allowed us to reverse the arrow and study certain Galois representations to construct concrete modular forms that we know should exist with a certain shape. Okay, so this is the motivation for me to look into this question. And then the final reason is, as I briefly mentioned before, is related to generalizing a conjecture of Harris and Venkatesh. And that finally. Conjecture. Here is Venkatesh. Explaining the action, the existence of the same systems of Hecke eigenvalues in different degree coherent cohomology for wave one forms, like a topic that in some sense Xi Ying introduced yesterday, to the context, to giving formulas for regulators of global points of elliptic curves. And in order to really get a good formulation of this generalized Harris-Venkatesh conjecture, the independence of P and independence of N that I was referring to earlier is really conceptually important, because we will end up formulating a conjecture that is essentially telling us that some quantity is maybe not well defined on the nose, but we can obtain it for different P's and different N's, and the ratio of those is well defined. Okay, so I will, if time permits, at the end I will say something about this. But for now, I'll stick to the generalized eigenvalues. And I'm going to say something about the Flach classes that Sarah briefly mentioned in her talk about Sarah and David's work about the symmetric square of an elliptic curve. So the setup is now that F is going to be a new form of level M. And I'm going to take a new form with coefficients in Q, so that the abelian variety attached by the Eichler-Shimura construction is just an elliptic curve that I'll denote by E. And I'm going to look at the Tate module of this elliptic curve. And I denote by rho the corresponding Galois representation. And in my talk, there will be an interplay between two representations constructed out of this that are very closely related. One is going to be the symmetric square of rho, and the other is going to be the adjoint representation, or zero rho more precisely, that are the same up to a Tate twist. So very closely related, but they will play a different role in my talk. So Sarah mentioned Flach's work on constructing certain classes for the symmetric square of an elliptic curve, and like the goal of this was like to bound the size of the Selmer group at zero rho by a construction of cohomology classes in appropriate Selmer groups. And this kind of question is like closely related to two important topics. So on the one hand, like studying this kind of Selmer groups that I will introduce now is related to modularity by the methods of Wiles and Taylor-Wiles. And on the other hand, this is related to statements of like Bloch-Cattel flavor. So there is an interplay between these two kind of constructions where that appears in the work of Darmon, Flach, and Galois, in which essentially the very similar groups appear and similar computations need to be done to prove, on the one hand, modularity, on the other hand, Bloch-Cattel sort of statements. But what is the geometric input behind this construction of the summer classes? So this will be a construction that is done at the level of modular curves, and then it will be pushed forward to an elliptic curve using the modular parameterization. So I take M my level. Yeah. Yes. Sure.
I'm sure it's true that Flach balance size. That's the exponent.
That's true. Yes.
I don't think there's any method in Flach's playing to balance the number. I think you get it.
No, that's true. You are only getting, yes. This was. Thanks. Yes. So, okay. So I'm gonna do like hint at a construction that will be done at the level of the modular curve of level gamma naught M, and that will be pushed forward to an elliptic curve via the modular parameterization. So the interesting thing is like what the input of this construction is. So the input is actually given by some units on the modular curve. The level of complex functions are simple. The discriminant function divided by discriminant applied to LZ. And this are in fact units on the open modular curve. And they will be viewed as units, no, not units, but functions. And after embedding the modular curve of level ML into two copies of the modular curve, by the two standard projection, whose image will be the Hecke correspondence at L. For L, here we are thinking of L a prime, not dividing M. Okay, so the input for the construction will be defining these functions over here, and this map given by the two projection defines a birational morphism onto the Hecke correspondence, which will give us rational functions and this Hecke correspondence inside the modular curve. And it's important to view this as a divisor in x0 m squared. So this is the geometric input. What we end up getting out of this construction is some classes in cohomology. So at the end of the day, we have to this ULs, one would attach a collection of cohomology classes that I'll denote as CLF, lying in a certain Selma group that for me is going to be the Selma group for the symmetric squared. I'm only interested in looking at this class as mod P for my purposes, in which I relax the usual Selma condition precisely at the prime L. So for each L, these classes will land in different Selma groups. And the Selma group I get here I can restrict at a prime that does not divide L or the bad primes for rho, and then end up in the unramified part of the cohomology. And now this finite part of the cohomology for each such prime admits a very complete description because it's going to be isomorphic to the cohomology of Fn with coefficients in sin square rho bar. So this ends up being a rather concrete group that could be identified with the co-invariance for Frobenius in here. Yes. N is a prime, yes. Yes. Just localizing, not doing anything special. I want to say that the image of the Flach classes under this localization map will tell me something about the generalized eigenvalues. So that's where I'm getting to. Huh? So I forget it. Sorry. It's all rho bar. So this is an important point to make. This construction is a construction of classes for like that ends up being a construction in H1 of K2 that can be mapped down with regulators into constructions in a tile cohomology with whatever coefficients. So in some sense, these Flach classes are pretty universal, and then there are a series of maps that send them to the correct groups. But here I'm content with just looking at mod P coefficients, but these are not mod P classes. Okay. All right, so I'm gonna state a few hypotheses, and then I'll state the theorem. So I want my residual representation to be absolutely irreducible mod P for P a prime different from 2 or 3. And I want to take this N here I wrote N as arbitrary, but I want N to be a prime such that I have level raising mod P at that prime. So I have that P divides N squared minus N plus 1 squared. I want this prime to not be a trivial prime for my representation mod P. So I want N to not be 1 mod P. And I want to make sure that all the congruences I get between my modular form and any new form of level N are generally congruences appearing at level N and not at lower level. And in order to do that, I can ask to take a prime that does not divide the degree of the modular parameterization of my elliptic curve. This is also a result that follows from Flach's work. So under these assumptions, I can state the theorem. So there is a unique system of generalized eigenvalues. Okay, I'll start. And again, unique here means up to rescaling, characterized by as follows. So my generalized eigenvalue is 0 if and only if the restriction on n of the Flach class is 0. And I can't quite say what, so morally, I would want to say that this coefficient is precisely the restriction on n of the Flach class, except that this doesn't make sense because this is not well defined on the nose. So I'm going to say that the ratio of two such coefficients is detected by the ratio of the Flach classes under this map. So, oh, thank you. So for if I take two different primes, so here we want a prime P L not dividing M and P. And here under the same assumptions for a pair of primes. I have the statement. I would want to say that the ratios are the same. That doesn't quite make sense, so I write it that way. Sorry? Star, thank you. Thank you. Yes, this is all about the generalized eigenvalues. Thank you. Yes. A number in FP. Yes, that's a number. Yeah, it doesn't lift to anything integral. It's purely a number in FP.
Beforehand, you had like a vector space. And
yes. Yes.
So what is the vector space deal?
So this would be, so these numbers will appear when looking at the action of Hecke operators. When I localize at the maximal mod P, when I localize at the maximal ideal corresponding to my residual system of Hecke eigenvalues, I can find the basis in which I precisely see these coefficients appearing. So the question is, what are the ratios for different primes? And the statement is the ratio for different primes are the ratio of the Flach classes under this map. Okay, so I would like to sketch a proof of this. Start from a different board. Yes? What?
Why are they called generalized eigenvalues?
Because I'm calling them that way because the action of Hecke operators on the mod P eigenspaces is is not semisimple. So we'll have generalized eigenspaces. So for this, I don't have like eigenvalues on the nodes. I'm looking at whatever extra bit I get somehow. Yeah, is the typical sort of situation that one should think of. And that's why I kind of put myself in the easiest possible situation, which the Taylor-Weiss method applies, and I'm guaranteed to have a congruence, and this congruence arises from level raising. Then most of the time, I can find a basis of the generalized eigenspace given by precisely two elements and do exactly the calculation that I was hinting at before for the Eisenstein setting, and it will tell me what coefficients I'm going to get. So try to sketch a proof. This is not a piece of paper. Yes. Yes. So I take a modular form at I take a new form that is not congruent to anything at that level, and then I raise the level at a prime n. So yes, so it's going to be, but it's important that all congruences that I see are congruences that appear for level raising and not for other reasons. Okay. So the first part of how to try to approach this and relate this to Selmer groups is pretty obvious if one has thought at all about modularity sort of questions. So by modularity, again, write my diagram again. So I have my Hecke algebra. I have a residual system of Hecke eigenvalues, and I want to lift it. To some lambda tilde. Well, if I'm interested in this, I might as well look at lifts of the corresponding Galois representations to this ring. So I'm going to look at representations rho, maybe rho epsilon of the form 1 plus epsilon some cohomology class that will depend on n multiplied by rho bar. So this cohomology class appearing here will be a cohomology class in an appropriate Selmer group. And I want to relax conditions at n because I'm expecting to have level raising at n. But this is going to be now a Selmer group for the adjoint representation, not quite for the symmetric square. Right? So it turns out that it's pretty easy to see that our assumptions combined with the work of Flach imply that this group is one-dimensional. Yes, everything is rho bar. Sorry. So this already solves the problem of like saying that there is a unique system of Hecke eigenvalues. Here there isn't much work to do. This is standard modularity kind of arguments. And now we want to compute the values of this lift, or rather the trace of the values of this lift at a Frobenius L for every L. Yes. Yes. Thank you. And now I want to compute the trace of rho epsilon of Frobenius L. And I'm interested in the collection of these values for every L, not dividing the primes that we don't want to consider. And when we write it down, this becomes the trace of, we can see that the generalized eigenvalues AL star that we're interested in up to rescaling will be given by evaluating this a representative of this cohomology class of Frobenius L and multiplying it by rho sigma L for every L. Okay. So how do we want to proceed from here? Now we want to play around with this and try to relate this with the Flach class. But before doing that, I want to do this in a much simpler case, like the Eisenstein case. And I'm going to give a wrong proof of the formula that I gave before. So, but that would suggest the right idea to approach this question. So, wrong proof of Mazur formula. Well, if I want to look at the Eisenstein case, I'm going to take my residual representation to be 1 plus cyclotomic and try to work that out. So I'm going to denote this by cyclotomic is the residual, the mod P cyclotomic character. And I'm going to write 1 plus epsilon A, B, C minus A that multiplies rho for my rho epsilon. Okay. Now, when I plug in Frobenius L in my formula, well, I can see that this will be given by something like 1 plus L plus L minus 1 that multiplies A. And A, because my residual representation was reducible in that with that form, would just be a homomorphism in H1 QFP. And if I'm relaxing conditions at n, I'll relax conditions at n here too. And at the end of the day, I will want to apply Frobenius L here. So for now, I'm going to take my cohomology class to be here, and I want to evaluate it this as Frobenius L. So this is going to be extremely contrived, but I can rephrase this evaluation, which is just applying a homomorphism as Frobenius L. as a local Tate pairing of what? So I take my class in here. I want a class in here. If I want a local Tate pairing, I want to look at the dual. And I want a class that depends on L. Well, a choice of such a class will be a class CL that is just going to be the image under the Kummer map of L. So I'm saying trivial things, but then when I write it in this form, I can take these two cohomology classes and rephrase this in terms of minus the local Tate pairing at n of the same cohomology classes. By global reciprocity. And now this has kind of the shape we want because this has to do with the restriction at n of a fixed class and the restriction at n of a class that depends on L. Okay, and how is this given as Mazur's formula? Well, this is basically saying that the image of this CL in the local cohomology at n will determine this value, but this is simply looking at the image of this in the finite part of the cohomology at n, which is isomorphic to Z mod and Z units, tensor with FP. Okay. So this will end up being the image of my prime L inside here, which is Mazur's formula. Now we want to adapt this kind of idea to the Flach classes setting. So we have one cohomology class for which we want to find the values of Frobenius L under this trace multiplied by Frobenius. And on the other hand, for every L, we have this collection of cohomology classes, which are very precise collections of cohomology classes. And we want to view the values we're interested in as values appearing from Tate pairing. So we want that the trace of sigma L multiplied by sigma L, which is what is responsible for our generalized eigenvalue, should be equal to some local Tate pairing at L between this class and the Flach class. And why this is true? Well, this has to do with how the Flach classes come about, and the fact that these Flach classes, and when looking at their restriction at L, have to do with Frobenius. So back to the Flach classes. We were interested in understanding the restriction at L of these classes now. Well, in order to do that, we're interested in understanding the units that we use to construct them at L. So the units UL that I introduced before are units on the open modular curve, but now we want to see them as functions on two copies of X naught, sorry, on the Hecke correspondence inside the two copies of x naught of n squared with coefficients over ZL. So what does this Hecke correspondence look like inside here? So I can imagine this as I want to look at the special fiber of these classes. So, okay, special fiber over FL. And this Hecke correspondence will, roughly speaking, look like two copies of this modular curve of level n. And I can view this as like the image, the graph of Frobenius on the one hand. I'm going to denote this as gamma L is the graph of Frobenius. And its transpose, pretty much the graph over Schiebrun. And what is important about the Flach classes is when we look at their divisor is concentrated on the special fiber and picks out exactly the difference of these two graphs. So the divisor of these ULs is, I want to be more precise, 6 times the difference is of these two. So we see that the Flach classes, when looking at its restriction at L, encode something that has to do with Frobenius. And when we chase this down under the right maps, we'll see that this is precisely the formula we get. Okay. How am I doing with time? 3 minutes or so. Okay, so I'm just briefly going to state say what the idea is in extending a conjecture of Harris and Venkatesh using this approach with Flach classes. So an elliptic version of Harris Venkatesh so this conjecture of Harris Venkatesh has to do with like systems of Hecke eigenvalues in multiple degrees coherent cohomology. And it relates them, it explains the appearance of the system of Hecke eigenvalues, of this Hecke eigenvalues via the action of a motivic group on the cohomology of Shimura varieties. The case in which I'm interested in is the case of the wave one modular forms. So that this action is the system of Hecke eigenvalues are in coherent cohomology, and the hidden action of this motivic group is a hidden action of like a much simpler kind of object, which is a group of units. So this becomes the action a group of units that are global units attached to a wave one form G and have to do with appear in the field in which the Galois representation of G factors through. So we'll have the action of this group UG. So Harris and Venkatesh formulate this general conjecture, but this conjecture really boils down to understanding the value of a certain functional in acting on the space of modular forms, mod P. And this functional can be characterized abstractly in a way as coming from an appropriate map defined over by viewing the covering of the modular curve of level gamma 1n to the modular curve of level gamma naught n. So this is Z mod and Z star plus or minus 1 covering inside the étale cohomology. Modular curve mod P here, and using this to construct a functional. But this functional can also be characterized more concretely on the space of modular forms. And it can be characterized in terms of this generalized eigenvalues. And that's why we were interested in understanding this question in the first place. So this functional is actually an Eisenstein functional, but more precisely, it ends up being a generalized Eisenstein functional in the space of mod P modular forms. So it's characterized by the property that a Hecke operator acting on this functional minus L plus 1 multiplied by the functional is going to be equal to this generalized eigenvalue that I introduced before in the Eisenstein case times the obvious Eisenstein functional in the space of modular forms mod P, which is given by taking a modular form and sending it to its degree 0 coefficient. So this can be purely characterized abstractly by saying what the Hecke action does to this functional. So we don't, for the elliptic case, and so the idea is replace the Eisenstein generalized eigenspace, Eisenstein with the eigenspace attached to a generalized eigenspace attached to the system of eigenvalues of a new form corresponding to an elliptic curve. So I'm going to say this as elliptic, and produce a functional that satisfies the same type of relation. And what the shape of conjecture we want to have is something like this functional applied to a product of certain test vectors having to do with my form G will be equal to, in the Harris-Venkatesh case, something to do with a unit in this mysterious group UG. And for us, it will be a 2x2 regulator of, instead of units, we got global points. on the underlying, for the underlying elliptic curve. So I'll stop here.
Okay.
Mm-hmm. Huh? I mean, it would be very interesting if there were one. We weren't able to make sense of it. And it would be interesting to understand if that is supposed to say anything about cohomology in that shape. But we went the route of making a much more naive sort of analogy in this sense. Yeah. That you can assume that your residual representation is going to look like, you can assume that it's going to be semisimple. Like, you have to argue that you can take it in the shape. No. Thanks.
Can you say a bit about this regular? This is a mod and mod.
So this will have to do with taking, roughly speaking, something that is in chalk. It's going to be a regulator of, I'm going to take for whatever splitting field we have for our representation, some global points of E, tensor it with the adjoint, and look at the part that is fixed under GQ. And this will map down to, we will make it map down to the seam square. I know that this looks weird, but that's what happens. Of the points over Fn squared. And now, whenever you can take a discrete logarithm of the points for this group, and you can look at the image of like a fixed set of global points. But the point is, like, there are a lot of choices involved in this, because you would have to choose a basis here. And what you can really try to say is that you fix your G and maybe your elliptic curve once and for all. You make your choices once and for all. And then you vary N and P. Because this is going to be a mod P conjecture that is not well defined, like on the nose. It's well defined on how it varies for N and P. And that's why it was so important for us to get a sort of formulation of this generalized eigenvalues that was in some sense independent of N and P.